Welcome to everyone who is in attendance today. We're going to have a special webinar with some special guests from University of Texas in El Paso, um, Jhonny Gonzalez and Shirley Moore. We're really excited to have them here today. They're going to be talking a little bit about some of the work that they've been doing on Chameleon specifically, and let me pull up my introduction here. I have a little bit better than this freewheeling. They're going to be talking about MINCER. This stands for the Monitoring Infrastructure for Network and Computing Environment Research. It's a user-built tool designed to address reproducibility challenges in HPC performance measurement using containerized environments and the PAPI PAPI framework to standardize metric collection across CPUs and GPUs. So the project is being led by faculty advisor Dr. Shirley Moore, who's with us here today, and is also being led by Jhonny Gonzalez, a researcher at UTEP, who's been driving a lot of the development. So I'm going to hand it over to him to take it away. And before I do that, I'll just make one quick announcement. We have, as you know, this is a full series of webinars that we've been running for about the last 6 months. So we will have another webinar next month. This will be on storage courselets, interactive materials for teaching storage systems concepts. So I'll drop the link in the chat if you're interested in signing up for that one as well. But today we got the MINCER team, so I'm going to hand it over to you, Jhonny, and you should be able to share now. I just gave you the permission, so
Yes, let me attempt to. Here we go. I believe it should be sharing, right?
yes,
Okay. Let me put it in presenting mode as well. Okay.
looks great.
So hello everyone. Let me move this really quickly. Uh, Here, yeah. Okay. So hello everyone. I hope you're all having a happy Mario Day, since it is March 10th. But good morning. My name is Jhonny Gonzalez, as mentioned, and I am a researcher at the University of Texas at El Paso. And today I'm going to be talking about a project called MINCER, right? And it does stand for Monitoring Infrastructure for Network and Computing Environments Research, right? So MINCER is a performance measurement and reproducibility appliance that we built specifically for Chameleon Cloud. And today, we wanted to go through why we built it, how it works, and what you can do with it. So for this project, we are going to talk about the problem it addresses, which I think a lot of system researchers run to at some point. And I hope by the end, right, you'll see the value of what we've built and how others may be able to use it in their own research. So I believe I have like 45 minutes to present today, right? And then at the end, we'll have questions. So let's move on to the next slide. So we'll start with the problem we're trying to solve, right? So reproducibility in systems research is difficult, right? So when we talk about reproducing performance results, we're not just talking about running the same code twice and getting the same answer, right? We're talking about the full complexity of modern computing systems. So, right, that's hardware architectures, software versions, compiler flags, operating system configurations, driver versions, runtime environments, and all of these variables interact with each other. And we know that if any of them change, right, it can lead to a dramatic difference in performance numbers, right? So, and that's not including GPUs, right, and accelerators. And when those get added, this problem becomes even harder, right? So, for NVIDIA and AMD GPUs, right, they have completely different software stacks, different driver interfaces, different performance counters, APIs. And we know that heterogeneous systems with multiple types of compute resources are increasingly common in HPC, right? But they do make reproducibility more challenging, right? So what happens is researchers often can't, they have a hard time comparing or trusting a build without spending a lot of time making sure that it's reproduced correctly, right? So that's a problem we see a lot in this field. So then, um, for before we go on to what we've made, why like we want to talk about why this problem matters, right? So it's easy to say that reproducibility is hard, and just move on, right? But what we see is when a researcher wants to build on someone else's published results, they do often have to spend a lot of time trying to get the environment to a state where they can run the original experiments. So even then, sometimes there's still things that are never quite sure if the setup is truly identical to the original, right? So on what we see on the HPC and GPU side, it's even tougher, right? Because the hardware landscape is very diverse. So you might get results from an NVIDIA A100 and you want to compare them to an AMD MI100, but there really isn't a standard way to ensure the measurement methodology is same across the two platforms. So we end up with a body of literature where results are hard to compare, hard to build on, and difficult to make sure they're done right, right? So researchers, right, they end up spending their time on environment debugging instead of uh, pushing productivity forward, right? And that's the core problem that MINCER is designed to address, right? So, right, let's go to the central challenge. So, to make it a little more concrete, the central challenge is that performance measurements are deeply dependent on three things: the hardware architecture you're running on, the software stack, including your operating system, drivers, compilers, libraries, and runtime environments, and the runtime environment, sorry, including permissions, kernel settings, and environment variables. And when any of the three things differ between the two experimental setups, the results may not be so comparable, right? And they often aren't. So without a consistent measurement tool, you end up in situations where you just lack transparency, right? And a paper might report a performance number, but without knowing exactly how that number was measured or what tools they used, what hardware configuration was in place, it's difficult to interpret or reproduce their work, right? So, right, like as I mentioned, it slows down scientific progress and makes collaboration tougher since, let's say, things aren't really one to one. And what we need to do, right, is standardize the measurement process itself, not just the code, right, that's being measured. So, what do we do? If we can standardize the performance and monitoring environments, we can dramatically improve the trustworthiness and comparability of results, right? So, a consistent measurement environment does three things. First, it improves reproducibility. So if everyone is using the same measurement toolchain, results from different labs and different hardware platforms become comparable, right? So second, it reduces setup overhead. Instead of spending a long time like trying to configure your software or match compiler versions, setting kernel permissions, a researcher can be up and running who know, maybe as soon as 30 minutes, right? So and third, it does increase the confidence in your results, right? So you know exactly what was measured and how. You can trust the numbers and build on them, right? And the underlying principle here is that researchers should be able to focus on their experiments and their scientific questions. So not just on debugging measurement infrastructure. And the performance data should be portable. So what do we mean by this? We want a result captured on a Chameleon node in Chicago, right? And it should be directly comparable to a result captured on a different Chameleon node at TAC, let's say, for example, right? That are located in Texas. So MINCER is our implementation of what we're trying to do. Um, so let's go on to the next slide. So what is MINCER, right? MINCER is a performance measurement and reproducibility appliance built specifically for Chameleon Cloud. Right. it's not just a library or a script. It is like a complete self-contained environment, right? That you can deploy on a Chameleon node. And Mincer is designed to do three things automatically, right? So set up the experiment environment, collect consistent performance metrics, and support multiple hardware types, including CPUs, AMD GPUs, and NVIDIA GPUs. All of them done within the same workflow. So the keyword is in Mincer's goal is reproducible. So we want experiments to run on Mincer today to be runnable again 6 months from now. And on a different Chameleon, it could be on a different Chameleon node by a different researcher and produce comparable results. So, right, it is difficult to do, but it is something that the research community needs to clear if we want performance results to be trustworthy and buildable upon. Okay. So, really quickly, the just to give a mental model of the overall architecture, uh, since it makes it a little easier to follow. Think of Mincer as three stack layers. At the bottom, you have the hardware layer, which is it's Intel and AMD CPUs, NVIDIA GPUs, and AMD GPUs. These are the physical resources that Chameleon provides, right, through its bare metal allocation system. And in the middle, you have the PAPI measurement layer. And PAPI has what are called components, which are essentially plugins that know how to talk to each of the specific hardware type, right? So let's say there's a component called perf event, which is for Linux CPU counters, one called CUDA component for the NVIDIA GPU metrics, ROCm for the AMD GPU metrics, RAPL for Intel power and energy measurements. And on top of all of that is the Mincer appliance layer, right, which is what you as a researcher actually interacts with. So this wraps everything in Docker containers so the environment is always consistent. It provides a Python render script that handles the experiment execution and automatically captures logs with timestamps and system metadata every time you run the experiment. So by let's say between the researcher and the raw PAPI interface, Mentor removes the need for you to understand the detail of each hardware component, right? So you just run the script and the right measurements right are automatically happen automatically based on what hardware is detected. So let's go on to the next one. So how does Mincer work, right? Um, the foundation is basically Docker containers. So we packaged like the entire measurement environment, right? So it has PAPI and all of its components, the necessary libraries, the correct versions of CUDA and or ROCm into a Docker image. And we make sure that the environment is identical every time you run an experiment. So, right, it doesn't matter if you're on a different Chameleon node or if you have the experiment run today versus 6 months from now, as I said before, the container is the same, right? And the second key component is PAPI itself. I will go over that in more detail in the next few slides, but PAPI is responsible for the actual hardware counter access. It's basically the engine underneath Mincer, right? So Mincer automatically records three categories of information every time an experiment runs, right? So it'll be the system metadata, which includes hardware types, OS versions, and GPU information, performance counters like cache misses, instruction counts, and floating point operations, and power and energy metrics from the GPU and CPU. The same scripts work across different architectures as well. So there's not really a need to write different code for a CPU experiment or versus a GPU experiment. Right, that's handled transparently. And let's go into the next slide. So what does it look like to use Mincer right from start to finish? Um, So basically, step one is provisioning your node on Chameleon. So what you do is you go into the Chameleon portal, find a node that matches your needs, which there's a lot right available. As we've seen, there's CPU only, NVIDIA GPUs or AMD GPUs, for just to throw in some examples. And right, you reserve that node that you need. That's where Chameleon's bare metal access really matters because PAPI does need direct hardware access to reach the performance counters, and that's not but that it could be difficult to do that, or it is very difficult, or not even possible sometimes, right, to do on a shared virtual machine. And step two, right, is just using the MINCER appliance, right? Get like putting the MINCER appliance into your bare metal node, as mentioned, and then step three is just running one of the four setup scripts, right? So there's one for each architecture. So there we'll have setup for CPU, a setup for CUDA, and a setup for AMD. And what each one configures, and each one, sorry, configures the environment automatically. So setting up kernel, it sets up kernel permissions, environment variables, anything else that PAPI needs to function, right? Step four is building the Docker image for your target architecture. So we do provide separate Docker files, and you could choose the one that determines which PAPI components are compiled in, right? So whatever, like whichever needs you have from PAPI, you decide that. So for step five, it's running the experiment with our Python runner script. So you do have to point it at your experiment directory with a path flag, and it handles the building, right? Which should handle the building, the running, and logging everything, right? So for step six, it's where you get your output, which is a timestamped log folder containing your results, right, along with all the system metadata that's needed to reproduce the experiment. So this whole process from provisioning to gathering your first results should probably take around 30 minutes, um, right? Which I think is very good compared to starting PAPI from scratch, which could take a while to like right get over that learning curve and trying to set up every single environment flag that's required where it's already done. So really quickly, like right, we've talked a lot about PAPI. So PAPI, we can now go over it, right? It stands for Performance Application Programming Interface, and it is a cross-platform library for accessing hardware performance counters. So it's been around for over 20 years at this point, and it's widely used in the HPC community, which is part of why we chose it. It is community validated, well documented, right? And PAPI does give you real-time visibility into what your hardware is actually doing. So, and not, it's not, um, it's sorry, PAPI's components architecture is what makes it powerful, right? For a project like MINCER. So each component is essentially a plugin, as I've mentioned before, that knows how to interface with a specific hardware or software layer. So for MINCER, we use four components. Perfivent for Linux CPU performance counters, CUDA for NVIDIA GPU metrics, ROCm for AMD GPU metrics, and RAPL for Intel CPU power and energy measurements. And this design does mean that adding support for new hardware type is a matter of actually adding or configuring the appropriate PAPI components instead of having to rewrite the measurement infrastructure from scratch, right? So right, PAPI actually does have a lot of components available, but these are the ones we're currently using for MINCER. But now we can actually look at traditional versus MINCER, right? So if you wanted to use, let's say, PAPI on a bare metal node without MINCER, first you'd permission your node as and install the operating system and all its dependencies, and then you grab PAPI's source code and build it from scratch. And that does include matching your compiler version to the PAPI version, making sure that the CUDA or ROCm libraries are linked correctly, resolving any build errors that come up, right? configuring system environment variables, adjusting kernel permissions, which right, and if any of these are missing, you will encounter many errors, or the measured data metrics will be incorrect, right? So it might take a while if you're not already familiar with these specific settings that are required. And right, for a new researcher, the process does take a longer time before they can even run their first experiments. But with MINCER, right, the workflow is essentially three steps, right? Pull the container, set up your experiments inside the container, and run it. And the container, right, handles all the complexity that would otherwise take a while for others to configure manually. All we've done, right, is the work of packaging everything correctly so that you don't have to. And the reproducibility benefits, right, are very valuable from this as well, on top of just assisting with packaging everything correctly. So again, why we've chosen PAPI. Um, the for the short answer, it's basically portability and trust. So what PAPI gives you is low-level access to hardware performance counters across a wide range of architectures through like a single consistent API. If you write PAPI code to measure cache misses on an Intel CPU, the same conceptual measurement is available on AMD CPUs and through GPU components on NVIDIA and AMD GPUs, right? You don't really need to learn how to use other profiling tools, right? Like NVIDIA SMI or ROCm, um, or perf separately. PAPI abstracts over all of them. And it also provides CPU and GPU performance metrics, right? Power and energy measurements, right? And it's very validated by the HPC research community for over more than 2 decades. So when let's say you're publishing your results measured with PAPI, reviewers and readers they understand what the numbers mean and how they were collected. So MINCER uses PAPI just specifically to ensure that we have two things, which is consistent metric collection, meaning that the same events are measured the same way every time, and comparable data across runs and platforms. So it means that a cache miss measured on a CPU and a cache miss measured on a GPU use the same underlying framework, right? So, which is essential, right, for cross-architecture studies that we want MINCER to enable. Here we go. Then we did include 4 proxy applications as example workloads. So these applications are used by the HPC community, right? And we have a couple of them, which I'll explain. And we have Axis Bench, which is a proxy for Carlo neutron transport, which is used in nuclear reactor simulation. It's memory and cache intensive, which right, it makes a great as a great test for MINCER CPU measurement capabilities. We have LULESH, which stands for Livermore Unstructured Langrendian Explicit Shock Hydrodynamics, and it's a computational physics workload developed at the Lawrence Livermore lab. It's compute heavy and runs on both CPUs and GPUs. We had a Gunrock, which is a GPU graph analytics library that provides data-centric programming model for graph algorithms. It tests memory bandwidth and GPU parallelism. And we also have 3D Unit, which is a machine learning workload. And specifically, it's a 3D convolutional neural network that's used for medical image segmentation. This one is interesting because it does use SciPAPI, which is a Python wrapper for PAPI that shows that right, MINCER's measurement capabilities do extend to Python-based ML workflows. And all of these 4 workloads have been tested on CPU, NVIDIA GPU, and AMD GPU platforms that we were able to access right through Chameleon. To right, demonstrate the MINCER's reproducibility um, throughout a diverse set of architectures and workload types. So here. Um, see, so as for a concrete picture of what data actually comes out of MINCER, Um, there are three, across all three architecture types, Mentor collects metrics in three broad categories. So from the compute behavior, memory behavior, and power and thermal behavior. On the CPU side, you do get classic PAPI counters like total cycles, total instructions, instructions per cycle, and cache miss rates at both L1 and L2. Plus, there's energy data from Intel's RAPL interface that's broken down by CPU package and DRAM. On NVIDIA GPUs, you get CUDA level counters for floating point operations, memory bandwidth measurement in bytes, transferred through DRAM, cache behavior at both L1 and L2, and system level monitoring through NVML, right, for power consumption and GPU temp. And on AMD GPUs, the ROCm and ROCm SMI components give you similar coverage, right? So GPU utilization percentage, vector and scalar instruction throughput, L2 cache miss hit rate, memory fetch and write sizes, and power and thermal data. So basically, what's important, it's not just the individual metrics in isolation, but the same experiment run across all three platforms does produce comparable structured output, produces comparable and structured output with the same method collected with the same methodology, right? And that's what makes this cross-architecture performance possible, right? And that's what we want to enable with MINCER. And so here, um, we worked with Chameleon Cloud because Chameleon Cloud provides with essential things that we need for Mincer, right? So first, we do need bare metal access, right? As we mentioned, PAPI requires direct access to hardware performance counters, and that is something you can't really do on virtual machines, such as, for example, like AWS or Google Cloud. The workload there runs on a hypervisor that abstracts from the hardware, and the PAPI's hardware counter access wouldn't be able to directly work with that environment. And but the good thing is, right, Chameleon gives you real physical machines with direct hardware access, which is what we need. Um, Another thing is we have full hardware control. So on Chameleon, you can actually configure the operating system, set kernel parameters, install custom software stacks, and adjust the system settings to match whatever experiment we require, right? And the this is essential for reproducible performance measurements. And third, Chameleon does support a diverse range of architectures, so they have a lot of Intel CPUs, AMD CPUs, NVIDIA GPUs, and multiple generations, right? So that's what allows us to use Mincer and to have it as a cross-architecture tool rather than being tied to a single hardware type. Thanks to the access of right, the combination of the bare metal access, the full control hardware diversity that we find in Chameleon, and it's great for us to have this have Mincer on these platforms, right? And we're happy to be part of the Chameleon um the researchers, right? And get their help. So for building and running Mincer, right? So basically, the starting point is always have a Chameleon bare metal instance, right? Reserve your node. Once it's provisioned and you're ready to go, you want to go into the command line. It's basically command line based everything from now on. So you download the Mincer appliance, right? And it gives you the full set of Docker files, setup scripts, example code, and the experiment runner. You from there you build the Docker image appropriate for your architecture. So there's a Docker, you'll find a Docker file for CUDA, one for ROCm, one that has the SciPapi Python wrapper, and one for CPU only experiments. Once you build this image, you run the experiment using the Python runner script, right? And you do have to provide the experiment directory where the runner will then handle everything from there. and it'll launch the container, set up the PAPI environment, run the experiment, captures the output rate, and writes the log files. So the results are automatically organized into time-stamped folders so that you have a complete history of every run that you do. And each log write includes a timestamp, system metadata automatically, it's captured automatically, and the full PAPI metrics output. This means, right, that if you do share your log folder with a collaborator or include it as a supplementary file in a paper, right, it'll have everything that you need for them to understand and verify your results. So for the output, um, right, we are gonna have a live demo, but really quickly, I did include a bit of an example output that you will see when using MINCER. So every time you run MINCER, it creates a new timestamp folder, right? So that you never overwrite previous results, which is intentional because you do want to be able to compare results across multiple runs, right? And it's part of what makes the tool useful for reproducibility studies. And inside that folder, you get two files. You'll have the output file, text file that contains raw output from the experiment. Right, it includes all the PAPI metric values too, and the execution log, which starts with system metadata that was captured automatically. That includes the operating system, CPU architecture, total RAM. And if you're on GPU node, it'll have the GPU type, memory size, driver extension. And this metadata is critical for reproducibility because it means that anyone who picks up your log file later can see exactly what hardware and software environment your results come from. So without having to ask, right, you. And then below the metadata, what you'll see is a full experiment output. I put an X's bench example here. It includes runtime in seconds, the energy measurements broken down by the CPU package and DRAM, the average power cycles, performance counters with derived metrics like IPC, and instructions per second already computed for you. The combination of system metadata plus structured metrics in a single uh, timestamp file, right, makes it portable, shareable, and comparable across multiple platforms. So let's go to a quick live demo here. So to save us a little bit of time, I've actually already compiled or yeah, compiled some things and have the Docker files ready. So really quickly, right here, let me get rid of that. Really quickly, I have them ready here too. So you do want to head into the Mincer package directory. Then from there, you want to run the Python script, right? And here is, right as we mentioned, you do have to pass the path to your working um, path, right? The experiment. Then you press enter. And while that's running, we can actually take a look at the what's under Mincer demo, right? Which I called it then. So we'll have like we mentioned, the Docker files which are appropriate for AMD, right? The ones appropriate for CPU. If you need SciPapi, or if you need some for CUDA, they're here. And we see that it already finished. What I ran here was the Lulesh experiment proxy app. And we'll only be covering the CPU side for today. But if you go under examples, right, there's the proxy apps that we mentioned. Here, oh, here we go. Lulesh, here. And we'll see here that we have the experiment logs. So here, right, at the bottom is the latest created run file log, right, where you'll have the experiment log as we've covered before, um, which you can see, right, that there's the comments on adding the PAPI events, and along with the metrics that we've discussed prior, right? So since we ran the CPU one, we got total cycles, total instructions, L1 DCM, L1 ICM, and right, the rest values. along with the instructions per cycle and the L1 cache miss rate. And the output just includes everything as well. Here is including right like what we solved for this Lulish example. I believe yeah, well you can see the problem size 96 with one MPI task. And something you do want to see, right, is you do have to have a run sh file inside of the experiment because this is what it uses, right, to know what we need to what parameters need to be set to run the actual experiment. But right, this is just a runner. Um, and yeah, that was the live example. It's as easy as that, just running these lines, and you've started right instantly gathering your data, as mentioned, along with um your metrics. Oh, wait, it was on this one. Uh-huh. Here. Oh yeah, here, the system information, sorry. Right, where it didn't detect the GPU since we used the CPU one, and I grabbed, as I mentioned, the OS, the CPU, and the RAM. Uh, and yeah, that's the live example. So let me minimize that and continue. Oh. Mm, Here. So so if we look at I have again the terminal output. If we look at it a little carefully, you can see, right, the simulation from the Access bench. Here I included an Access bench, right? So for this example, but it does confirm that the workload ran correctly, right? And we can see the energy and performance monitoring initialization messages. So we have PAPI starting up, and we have it confirming that it successfully initialized the measurement environment. The simulation right then runs, and then at the bottom you get the results. Right, so we have a runtime for the access bench configuration. We have energy measurement section for the CPU. Um, we have the DRAM energy reported as well separately. And I mean, it is useful, right? Because sometimes memory access is often a significant component of total system energy for memory intensive workloads. Right. And we have the total energy as well, along with the average power. So in the performance counter section, you can see the total cycles, the total instructions, and the detected CPU frequency, the instructions per second in MIPS, MIPS, and IPC, and the instructions per cycle, sorry. And so this is right the kind of insight that we're able to give with MINCER, and we're able to surface it right using our tool. So let's move on. So we do have a table, right? Of a couple of things that it's just some examples of a table we created easily just with the metrics we gathered, right? And just I mean, this really didn't take long. As I mentioned, we just ran exactly what we needed. It probably took no less than an hour to quickly grab some values and create a table. Running the same experiment, right, which is X's bench with CPU, NVIDIA, and AMD. Um, so what we use most, right? So basically, the hardware catalog is something we use constantly, sorry. So when you're running cross-architecture experiments, you need to know exactly what hardware is available, right, and where. So through Chameleon's catalog, it easily helps us identify what nodes have AMD GPUs or NVIDIA GPUs, along with what GPUs are available, and along with what CPU specifications look like. Right, and this is essential for planning experiments and documenting the hardware configurations, which we do in our logs. And we can also do some bare metal reconfiguration, which is another feature that we depended on heavily, right? So we can re-image a node with specific operating system configs, right? which means we can ensure a consistent hardware baseline across runs. So if we run an experiment, right, let's say today, and we want to run it next month, we can provision a node with the exact same type, image, and be confident, right, that the hardware configuration is comparable, and along with operating system level access, which is a fundamental, right, for MINCER. And so like you can install custom versions of PAPI, CUDA, ROCm, configure kernel level permissions, which is only possible, right, through Chameleon, which gives us a great OS control, where we would have a hard time making MINCER work without it. So what we find a little difficult, it's that the performance studies of this kind for MINCER enable for it to enable, it requires three things, right? OS control, stable hardware, precise measurement capabilities, wherein like as I mentioned before, uh commercial the like other ones such as AWS or Google ones, right? Well, you'll just get some virtualized hardware. And as we know, right, PAPI wouldn't work on these. And on traditional HPC systems, you do have more direct hardware access, but you typically don't have OS level control. Like so you're basically working in a shared environment where you do have system admins that control the software stack, and installing custom versions of certain things such as CUDA, ROCm, or if they already have PAPI for you to load. It's not something you can do easily. Um, and right on these platforms, you don't get the combination of diverse architectures of CPUs, NVIDIA GPUs, and AMD GPUs, which are all accessible through the same, well, you don't get them all accessible through the same interface and management system, right? And Chameleon does provide all of the things we need. So, Um, here we go. We are currently we have everything on a GitHub, and we're working with Mark, right, to like we're just tidying everything up and having it ready to give right to Mark so that he can share with the Chameleon right community, and as hopefully you guys are able to use it, and perhaps we can even put it as an artifact that right, anyone could just rerun if they wanted to, um just right, so we can have it better for best reproducibility, which is right where we're headed. um and lastly, who benefits from MINCER? Here we go. hmm So basically, right, we have researchers, right? So everyone will have a easier setup, and along with um, included trustworthy results. The students who learn performance analysis with hands-on, so they get to test. They actually get to use PAPI, right? The PAPI setup we have, and just automatically know or have access to complex setups, right, that we have, that PAPI allows us to do. And the HPC community, which more broadly benefits from having a standardized tool that produces comparable results across right, different institutions and hardware platforms. So if two research groups at different universities do end up using MINCER, the results are directly comparable, right? And in many ways, and the right Chameleon users who benefit from faster onboarding for systems experiments, right, instead of spending let's say like a week trying to learn how to have everything set up, you can just spend that week doing pushing yourself to have increased productivity without having to face any debugging issues, right? For the first week, which many of us have been there, right? And right, what we want you to remember, I'll just close it off by saying that right, reproducibility is a costly problem that we see a lot in systems research, right? It's not It does slow down productivity a lot. It does have like, let's say, published results have a hard time. Well, we have a hard time reproducing published results, and it makes collaborating a bit tougher. Right, and MINCER just provides a practical working solution, right? So we have a containerized measurement environment that works across CPUs and NVIDIA and AMD GPUs, and it produces portable and comparable output that can be up and running right in probably less than 30 minutes. And none of it would be possible, right, without Chameleon Cloud, where they give us bare metal access, the hardware diversity, the full operating system control that Chameleon provides, which is very essential. And lastly, right, the performance visibility, which leads to better science. So when you know exactly how much, let's say, your energy, your workload consumes, how many cache misses are generated, the IPC, what it looks like on each architecture. You can actually use those to make better research decisions and write better papers, right? Since you build more efficient systems. So that's our goal with MINCER. And thank you for giving me your time. And that's it. Mhm.
Wonderful. Thank you so much, Jhonny.
Mhm.
That was a great presentation. This is really interesting. I think it's fascinating to see what you've been doing with all this stuff, and I can certainly see the value in it for a lot of people who are using Chameleon. Um, we
Thank
have
you.
a couple of questions, so I'm gonna pause the recording or stop the recording now so that we can everyone can ask questions without worrying about what they're saying.